Alright, so this is take three. I've been having some problems finding a recording software, so hopefully this trial of a very expensive recording software does the trick. So hi, my name is Nicholas Bergez. I'm in Group 2 for Computer Science 550 Programming Languages, Spring Quarter 2016. And this is the first part of our group term project, on expanding mini languages. Um, my section is on Chapter 5 of Programming Language Pragmatics, Target Machine Architecture. We're going to go over it. Um, so this chapter, the author covers the topics of computer architecture most essential to compiler construction, namely memory hierarchy, data representation, and instruction set architecture. He then covers the four largest paradigm shifts in architecture and how they impact compiler implementation. And then last, we discuss modern compilation issues for today's processors. So first up is memory hierarchy. Memory on most machines consists of a number sequence of 8-bit bytes. The size or number of distinct locations is limited by the number of bits used to represent an address. For 32-bit systems, it's 4 gigabytes, and for 64-bit systems, it's 16 exabytes. This much memory can't be put on a single chip, so they have to move the memory to different locations on the computer. This raises a problem that the farther away the memory, the longer it takes to reach the CPU. So to solve this problem, they invented a memory hierarchy, which keeps frequently used data close to the processor. This consists of registers, cache, and devices. The registers hold small amounts of data and are accessed very quickly. They're managed directly by the compiler, and it spends a great deal of effort to ensure that the most frequently used data is always in registers, minimizing main memory access. Caches are designed to exploit locality, the tendency of most computer programs to access the same or nearby locations in memory repeatedly. Caches are maintained by computer architecture and are usually split into multiple levels, each larger and a bit further away from the CPU. L1 cache is the smallest, going to L2 and L3, or even more, and further from the die. Should a piece of information not be in the registers, the CPU looks at L1 cache, then L2, and so on, until it finds it or it misses. If it misses, then the main memory access is required, which is the slowest operation. Figure 5.1 gives us an idea of how slow that is, where the registers and caches are in nanoseconds. Main memory is significantly slower, and then if you get to flash drives and disk drives, they take up to micro and milliseconds, which is in an entirely different realm than nanoseconds. The next section, he talks about data representation. Data stored in memory is simply a string of bits. The represented data has no type. However, operations do have a type. The data is interpreted differently based on what is going on. We'll see how it deals with integers and floating points here. Integers come in half-word, word, and double-word lengths. Floating point numbers come in word and double-word lengths, referred to as single and double precision. And data can be stored either with the least significant bit first, little endian, or the most significant bit first, big endian. This used to be sort of a holy war among computer scientists. For instance, I usually, when I write things in binary, is in big endian. But I can still read little endian, and compilers are able to figure it out, and so it's becoming less of an issue. For integer arithmetic, integers are represented in two formats: straightforward binary, or unsigned 2's complement for signed numbers. As we can see in figure 5.4, it shows us the two complement numbers. the first bit is, if it's a 0, it's positive and it reads like a normal number. And then if the first bit is a 1, then it's reversed. So like all ones is -1, and then you flip that 0 and it's a -2, etc. The biggest thing that a compiler has to worry about is if we add two positive numbers, if it overflows into the last bit. Some machines generate a fault, some have a testable bit. The compiler just has to be cognizant of which one is which. For floating point arithmetic, it's basically scientific notation in the bits. They have a significand, or a sig, and an exponent, exp, and a sign bit. As we can see in figure 5.5, it shows us some of the single precision and double precision floats, how they're stored in memory, and then some of the things the compiler has to be worried about. We can't really go into too much detail of floating point arithmetic, as it could take an entire course to go over, but the compiler looks for is the zeros are represented by a bit pattern of all zeros. There are 2-bit patterns reserved for positive and negative infinity. They have a bit pattern for not a number, and the patterns used for non-negative, non-NaN float numbers are ordered the same as integers. In the next section, he talks about instruction set architecture. The instructions on a machine and their encoding in machine language are referred to as the instruction set architecture. They vary a lot between implementations, but they all have instructions for computation, data movement, and control flow. There have been shifts in ISA thought over time. They started with a complex instruction set computing, which sought to maximize the useful work performed per instruction, and went to a reduced instruction set computing, RISC, which seeks to maximize the number of instructions that can be computed per second. This isn't much of a concern anymore, as CISCs, they're translated into RISCs for pipeline architectures. The big difference between the two are how the addressing modes and conditions of branches are handled. The addressing modes have two different ones. There's displacement addressing mode, and index addressing mode. For displacement, it takes a base register that contains an address value and then adds a displacement value to it to find something's address. For indexing, one register has the address of an array, and the second has an index, which contains the offset for that element. Conditions and branches, one way they can do it is via condition codes, which are implemented as bits in the processor status register, and the code determines what is executed in the program. The other way is predication. The system translates all the if-then-else into branchless code, and then it has a code prefix to each thing, and it either executes something or makes it a no-op based on what that code is. The next section, he talks about the architecture implementation. During the life of computing, there have been 4 main architecture paradigm shifts that have affected compilers the most. The first one was microprogramming in the 1960s. When they developed new hardware, it fundamentally changed the instruction sets, which required programmers to relearn a language to continue programming on the new platforms. The breakthrough of microprogramming allowed companies to give the same instruction set across the whole line of computers. The instruction set, in effect, abstracted the architecture. This also allowed programmers to extend the instruction set for a given architecture. The next one that impacted compilers were microprocessors. In the 1970s, very large scale integration, VLSI, reached a point where they were able to finally put an entire microprocessor on a single inexpensive chip. This allowed for commercially viable personal computers to be achieved. The next thing is the reduced instruction set computers. In the 1980s, several factors converged to create the next breakthrough, RISC. The first factor was VLSI improved to the point where they could fit an entire pipeline on a single chip. The second one, the processor speed, started to greatly exceed memory access speed. Third, compilers got to the point where their output code was equal to or quicker than highly optimized assembler created by professionals. These allowed the reduced instruction set computers to be an idea that gained a lot of steam. As opposed to its counterpart, CISCs, it strove to have lots of single instructions that finished quickly instead of reducing the number of calls with large complex ISAs. The next paradigm shift he covers is multi-threading and multi-core. Moore's law stated that since the computers have been a thing, we've been doubling the number of transistors on a chip every 2 years. The increased transistor density was used in 4 different ways. The first was faster clock speed. The second was instruction level parallelism, which the third was speculation, which is the processor predicting which branches would be run and then pre-executing them with a rollback mechanism. And then the last way was to make larger caches. The first 3 ran into a dead end around 2004 as the heat on the processor die couldn't be dissipated efficiently enough or cheaply enough without expensive refrigerating systems. Because of that, they decided to go towards multi-core processors. With these multiple cores or processors, the system can run multiple things at once. However, this means that programs needed to be recoded to take advantage of that. The other drawback of that is kind of an abundance of riches. If you have 1 or 4 cores, they can all be kept busy pretty regularly, but if you have 16 to 32 or 100, they do not have enough stuff to do to keep them all busy. He then talks about issues for compiling with modern processors. So programmers today would have a very difficult time coding assembly for it. Luckily, our compilers don't get bored or make mistakes. They usually use a small subset of the RISC instruction sets to facilitate optimizing the code. The real difficulty they have doesn't come from using primitive instructions, but from keeping the pipeline full and making good use of the registers. They keep the pipeline. There are 4 main problems that can cause a pipeline to stall: cache misses, resource hazards, data hazards, and control hazards. Cache misses are something isn't in the cache and it has to go load it from main memory. Resource hazards are 2 instructions may need to use the same thing at the same time. Data hazards, an instruction may need data that hasn't been produced yet. And control hazards, the branches that are in the code aren't determined until the conditions are evaluated, and that could change the way things are ran. These issues can be avoided on both the hardware and software side of things. For hardware, they can make increasingly complex circuits that attempt to circumvent these issues. For software, the compiler attempts to optimize the order in which the instructions are executed. For in-order processors, they need to identify a valid order that will minimize pipeline stalls at runtime. For out-of-order processors, they need to maximize instruction-level parallelism, the degree to which unrelated instructions lie near one another in the instruction stream. The other way is register allocation. Um, so when we move data between memory and registers, it's expensive. Cache hits take a cycle, and cache misses can take dozens to hundreds of cycles. That means the compiler has to try to use as few loads as possible, and they do this in a two-stage process. The first stage is the compiler identifies the portions of the abstract syntax tree that represent basic blocks and assigns a virtual register to them. The second stage, the compiler maps those virtual registers to actual registers on the CPU. When it has to, it will write registers to memory, and when they aren't able to be mapped. So in conclusion, in this presentation we looked at the 5th chapter of Programming Language Pragmatics, and he investigated how compilers interacted with the target machine architecture. We discussed the machine's memory hierarchy, the data representation, the instruction set architecture, the architecture's implementation, and how compilers handle compiling for modern processors.